Okay, thank you, Franco, for that kind introduction. The topic I'm presenting is UV fluorescence. I want to first tell you what we don't want to do. After I introduce also the people I use results from, which is Daniel Meyerhofer, who works in Austria in a company, Gustav Uberi of AIT, and Gabriele Eder from OFI Wiener Neustadt, also in Austria. Most of the research done here was developed in an Austrian national funded project in Amstel with project partners like OFI, ENCAM, Ecostodia, and so on. So let's really get into it. The UV fluorescence, probably you know it from things like looking at fancy minerals or discotheques where you have the UV light, or of course our all popular drink, tonic water. What's going on there is that basically UV light comes, typically UV light, and kicks off some electrons to an excited state, and they then fall down from excited states towards the ground state and emit a photon. And this photon, in some useful cases, can be in the visible range. If this is the case, we can see it with the naked eye. There is also the distinction between fluorescence and phosphorescence, where phosphorescence happens when the electrons get moved into a state where the decay takes a long time, in a forbidden state, and then you have delayed emission of photons. This is useful for warning signs or clock hands, old-fashioned clock hands. This is not what we are talking about here. We are looking at photon emission directly. When we illuminate with UV light, if you turn it off, it's gone again. How can we use this for photovoltaics? The most common way is to emit the incoming light with a laser or a lamp or something and look at the spectrum at given points. And then what you can see is the material below is emitting something in ER, typically for polymers. This is also not what we're going to look at. We will look at imaging, which is a sneaky way around having to own a spectroscopy setup. If you have a typical layering of a glass backsheet module, you have the front glass, you have the cell, you have the backsheet, and all the gooey stuff in between. That's the typically EVA or polyolefin or some polymer basically that glues everything together and gives also some kind of protection for height deviations in the cell, so things don't break that easily. Now, the next slide. What happens is that UV light goes partially through the front glass, and heat originating from the cell, because if there is solar radiation, only 20% get used and the other 80% heat. So what you have here in the EVA is heat and UV light, and this creates some molecules that will have fluorescence. I have to be quite vague here because molecules, yeah. What is currently the basic estimation what could be fluorescating is not completely clear to me. One typical molecule that fluorescates is carboxyl groups. This you can have in the polymer. If it's damaged, this could lead to fluorescence. Yeah? What could also happen is that it's the additives. The additives are for sure somehow linked to the whole thing. There are, for example, UV absorbing additives in there that change quite dramatically the amount of fluorescence that you will get. We have tried multiple experiments where we try to understand what will create fluorescence, what will remove fluorescence. We are not the only ones who did that, and it's not completely clear what happens, to me at least. What, however, happens is that once you have a fresh PV module out in the field, sun comes, heat comes, and it will start to fluorescent. However, with time, also oxygen, water, or some other substances can diffuse through the backsheet, and by some photochemical process probably remove again the fluorescence. So at the side of cells where you have a clear diffusion path, a fast diffusion path, you will typically see in the fluorescence images that I will show later on black stripes. And this is very useful in the end. Even if you don't know if it's oxygen, if you don't know if it's water, or if it's photochemical, what we can see is gaps. And this will also happen at cell cracks. If we have a crack here, this is also an additional diffusion path, and you will be able to see, if you radiate with UV light, with the naked eye, you will see the fluorescence photons, and you will see dark areas and no fluorescence where you have cracks in the cell. And this is the main mechanism that we find useful for this method. There has been a lot of research going on for multiple years, not only from us, but also, of course, from Mark Könkes, the Beate Röder group in Germany with Jan Schlotauer, even older papers like Pern. And here I give you a short collection of papers. There are a lot of them, mostly from these typical writers. It takes a few seconds to the slides update. There are also some papers in German. Come on, update, please. Yes, because a lot of people who do this research are in German. There are some German-specific conferences, like the Bad Staffelstein workshops and so on, and there are also some stuff there. We also did a diploma thesis that I'm not sure if you can download it. If you want it, it's in German. I can distribute also, where we compared this new technique that I will show later on with thermography mostly. That's this paper here from Daniel Meyerhofer. So what we need to do, we need to illuminate the PV module in the field or in the laboratory, but preferably in the field with UV light. And in order to excite the fluorescence, we need to go through the front glass. So it must be of a wavelength that is transmitted through the glass, because otherwise the glass absorbs everything and we don't see anything. So this is the one prerequisite. And if you do this, you can take 400 nanometers, for example, and just use an LED and illuminate the whole thing. You will see the brighter regions where you have the fluorescence and the darker regions where the fluorescence is omitted or cancelled out again. This is already useful, but what you see here is really bad contrast, because all those LEDs, they also emit in the visible spectrum, which you then perceive as violet. And everywhere you have this violet light, and this decreases the small output that you get in contrast from the fluorescence. Also, if you have just one LED, it's quite difficult to make it homogeneous, to get nice pictures, to see larger areas and so on. Yeah, this I already told. If you look at the spectrum of a normal LED, you will see that even a laser has a bandwidth that you might even see with naked eye. With LEDs, it's the same. So there you need to do some filtering to get optimal contrast. And this is why it's not so trivial to build an illumination source for this. If you look at the spectrum, and this will be the only spectrum that I will show of the fluorescent light. If you have 400 nanometers, you illuminate, and then you measure different locations of a cell. You see that typically you will have fluorescence in the blue spectrum. And then in the regions where you have no fluorescence, you have the blue signal. The green is if you have normal cell fluorescence. And then if you have a hotspot cell, you will have much brighter fluorescence, which is also in the brown region. And this is quite common. There seems to be two, I wouldn't call this a peak, but two sections. One is normal destruction of EVA or altering of EVA or the encapsulants, we can't distinguish at the moment, which is happening in the blue spectral region. And then if you have thermal damage, typically this is in the brown region. And I personally believe that this brown region, if the thermal damage gets worse and worse and worse, correlates with visible browning. But I have very little statistical evidence for that, I have to admit. So if you have just one LED, you also can illuminate only a short section of the PV module. And it took us quite a while, and as I would say 6 or 7 iterations to develop a lamp that you can use. Of course, you can also build yourself a lamp, but you can also get it. Where you have UV LEDs, a lot of them, distributed over large areas, so you have homogeneous illumination. This is not the only system that you can get. Also, Mark Köntges developed a setup where he has a tent that you can put over a module, which also works in the daytime. And this he presented at a TÜV workshop in 2015. If you use this, you will get high contrast images like this one here, where you see a lot of stuff. If you can see the mouse pointer, the left cell here, in the second row, this is a typical cell. So you have fluorescence in the center, in the core, and then at the boundaries, what you have is black stripes. And these black stripes they would be fluorescing normally, but due to the diffusion from the backside and some photochemical reaction, the fluorescent gets destroyed. And this also happens here at cracks. And here you have got a lot of cracks in this module. Not sure why, probably snow load or something like that, or mechanical load testing, I don't remember exactly, but you see a lot of cracks. What you can also see here on the left side, maybe a bit weak, is that there is a second sheet behind the busbars here that is typically put in to have isolation in the section of the junction box, at the collection of the wiring, basically. If you look at a hotspot cell, update. What you see here is a hotspot cell that even has visible brown. So it was really in the field for a long time, was getting really hot, and the cell became brown. There are some short circuits here where you see even the oxidation of the cell surface and so on. And this cell, it's remarkably more brighter than the other cells. Because here you also have this red spectral range where you have the thermal damage. And if it's seemingly warm, it improves the production of these fluorescent molecules. This is again the module that we've seen 2 slides before, but now it's full screen. And I would recommend that everybody picks his preferred crack. I will, for example, take this one here on the left side. And then I will switch to the next slide, which is the corresponding EL image. And here, again, you can see in the EL image that there is a crack. It's a bit faint because there is less contrast in the EL image. And I will go once again back. Maybe you want to pick a crack from the EL image that is clearly visible. And I go back to the UV image, and it will be there, quite sure. So there is a strong correlation between the cracks that you can see in the UV fluorescence and the electroluminescence. And it's even, in some cases, it's easier to see the cracks in the EL because they have higher contrast. In the UV, sorry. At this state, this was the state 1.5 years, 2 years ago, we didn't really know whether we had a few modules, the fluorescent, in the laboratory from outdoor testing that came to us from diverse projects. And we wanted to know if a typical PV plant outdoors will show this fluorescence. And we investigated 6 PV plants in the surrounding of Austria, of Vienna. And in each plant, we saw this fluorescence with different intensity, however. Seemingly, the intensity depends on the mixture of the EVA. So for this test, we wanted to know what we can use UV fluorescence for. What's the best use case? And we compared it with the most common method with thermography. I will wait so the slides can update. Yeah. So thermography, of course, you do under the day. If it's warm outside, clearly it's sunny, you do it. The UV fluorescence, you have to do at nighttime. So it's not possible at least with our system, to use it in the daytime, because the UV light emission is quite weak, and the response of the module, the fluorescence, it's even weaker. But you can see it with the naked eye quite well if it's dark outside. For these plants that we investigated, we were not allowed for insurance reasons and practical reasons to do any changes to the electric circuitry. So all we had to do was passive. So we couldn't do EL imaging of the system. And this is then what we get if we take a camera, do a long-term exposure, so we can emulate the very good efficiency of the human eye. Then you can see outdoors the cracks in the modules with the naked eye. And you can just walk around, illuminate different sections, and see the cracks there. That's where we thought, okay, quite interesting. Let's see how it compares to thermography and so on. So here, for example, in the more right module from the middle, you can here clearly see some cracks. You can also see other things like the intermediate backsheet layer that is put here that I mentioned earlier. You can see some brighter spots here, which might be dirt, because a lot of dirt is also fluorescing. This is a different section where you see here that if you don't hold the lamp right while making the exposure, there will be stray light, and this is stray light from the movement of the camera. So this is typically what you see. You see some stars here. It was not completely dark. You see the backlight illumination is because of the urban light in Vienna. You can see even cracks in monocrystalline cells, which are typically diagonally. I will wait for the slide to update. Yes. What you also can see sometimes is that the busbars are brighter or fluorescing. Sometimes there are sections of the busbars who are not fluorescing. Again, wait. Maybe I should tell I have a laptop next to me where I can see what you see. So I have all the delays. So here in this picture, you see that the busbars are extremely bright and fluorescing. You see the black bars around the cell, which are quite thin here. And you see in some section of the busbars, it's dark. Which is, well, it's a bit strange, huh? Honestly. The expectation that we have, I will explain later on. Then we assembled this to the whole tables with Photoshop to make direct comparison to images that we got from thermography. So we took millions of thermography images, no, not millions, but a lot, and assembled them, and then compared it to the UV imaging. I will wait for the slides to update. A bit too fast, I guess. Yeah. This is a typical UV image that we do with a 1024 camera. With here, you in this case see a bypass diode that is failing. And we also did the same stripes where we just make the flat assembly of a table. And this we then compare directly to the UV imaging that we done at night time. And it turns out that you see a lot of things with the UV imaging, maybe 20 times as many defects, but most of these defects are not really critical, because critical would mean that you would see them in thermography. If there is a failure that doesn't produce energy, or where a module is not able to take out its energy by electricity, it will heat up. So all the failures that you see that are energy critical, you will see with thermography. And these are very few compared to the failures that you see with electroluminescence. So yeah, next slide you will see that the tables were quite large. We investigated really a lot of modules and cells for this. In some cases, we found correlation where you could see a hotspot in thermography. And of course, in the UV fluorescence, you will see that there are cracks in this cell. at this position. But it's not the only crack. So here on the right-hand side of the module, there would also be a crack, and you have no correspondence here. Or at the top right corner, you have broken cell, but you see absolutely nothing in the thermography, which means that only this cell is the weakest link and heats up. We try to correlate the position of the UV findings, which is quite common, that you have this cross-shaped pattern, which is in the next slide. So in the corners, most often the cells are broken. There are also papers of Mark Köntges, like 3-4 years ago, that presented in Bad Staffelstein and PV-Sec, where he showed transport problems of PV modules, and that mostly the cells in the corners are broken. We also found a defect where you have a dark spot in the cell somewhere, and this also seems to correlate with corner positions. That we call that freckles at this stage. I will come to that later. Yeah, here you've got the cell cracks. It's also in the corners. And then we have a defect that I will also show later, where the area around the busbars is darkened, which I will come to that later. Here we see that in different PV parks, different arrows show with different probability. So cell cracks, these plants were quite good in my opinion. Typically I would estimate that 5% of cells might have a crack. Here we had typically 2–2.5%, which is really nice. The busbar darkening, this happens only one kind of module that was mounted in one PV park. The dark spots were mostly visible in a different manufacturer. We tried to estimate how much time we spent doing the evaluations, how fast UV fluorescence is compared to thermography, to understand if it pays off to do UV fluorescence. So we had the initial costs, we did the calculations even with travel costs to go to the plant and so on. And we come then to this graph in the next slide, where we have here the park size in kilowatt peak on the x-axis, and in the y-axis we have the typical cost of investigating this park per kilowatt peak. So of course, if the plant gets bigger, you save some cost, but then again you have to work longer. There's a big difference between how well you want to document. If you want to do good documentation, you need to write a report, you need to monitor exactly where you have taken the picture and so on. Even with the thermography, it's a lot more work than if you just run through and look and mark modules that have problems. And if you just run around and investigate things, UV fluorescence is faster than thermography, in my opinion, because it takes less. You can just run through in a really running speed. However, with thermography, you have to look through the camera, and so you have to turn, look at the camera, and then turn back and go on. Because if you look through the optics of the camera, you can't really walk. So it's a bit faster, and this, I think, makes it feasible. The disadvantage is again that you have to work at night, and yeah. So I think it's comparable, but you don't see the same things. Here we did a comparison of the two systems. So if you want to take a picture with UV fluorescence, it takes you 20 seconds, but you get a 24 megapixel if you have a good camera then. While with thermography, you get low resolution pictures, but you have short exposure time. So, of course, UV fluorescence you have to do at night, which sometimes prohibits the use, because at some parks, maybe at the roof of a supermarket, you probably wouldn't be allowed to be there at night, or you would have to convince a lot of people to be allowed to be there. But again, it's easier to plan that there will be darkness. For thermography, you have to have a clear day with ideally no wind and no clouds, and you can have the weather forecast, but it's not as plannable, in my opinion. In thermography, you have a small angular dependence that you might ignore probably. And what you do with thermography, you can see bypass diode failures. So far, we haven't been able to see the temperature increase that you would get if your bypass diode fails in increased fluorescence in a third of a module. We haven't seen this so far, which is a bit sad. PID, we could not see any evidence of PID with UV fluorescence, while with thermography, if you look careful and you are able to monitor small temperature changes, you can see that. Yeah, as I said, darkness is easier plannable than brightness and no clouds, which makes the UV fluorescence quite feasible in wintertime, because it gets dark quite early, so you have long nights. You can just walk around, while thermography, for example, would be rather feasible in summer. In winter, you might have fog, you might have low air radiation. So thermography, I would say, for summer. UV fluorescence might be rather for winter. What you can also do, very often, manufacturers of PV modules change their materials. However, if they would change the materials, legally they would be required to recertificate the module. Very often they don't do that. And with UV fluorescence, if they change the EVA or the backsheet, very often you see big differences in the thickness of the dark areas in the UV fluorescence or the total brightness. So in one part, there was one module next to the other with maybe 5 times brightness difference in the UV fluorescence of the same manufacturer of the same module type. And I'm very sure that if it came to problems with the modules, that this would be a good option to put pressure on the module producer. What you can also see is difference according from the backsheet. This was found out by Gabriele. She, from chemical analysis, she knew that polyamide has much higher oxygen permeability than Tedlar. So oxygen can diffuse faster if you have this polyamide backsheet, and Tedlar less. However, both have nearly the same diffusion rate transmission for water vapor. And you can see here that these modules, we know for sure that they were mounted at the same time in the same location. And you can see the thickness of the dark areas is much wider with the polyamide, which is an indication that in this case, the destruction of fluorescence at the gaps of the cell is probably linked to the oxygen diffusion. However, we also have seen other indications that water might be a big factor, or even glue. If you stick a sticky tape to the backside, it will also change things. Now we'll come to a section where I'll show you more in detail what errors we found after the slides update. So here we have a cell that I would say which is perfectly all right. You have, so the module went outside, it started to, with time, with temperature and UV exposure, it started to change the material a bit in the EVA and started to fluorescate. Then from the sides you had the diffusion of oxygen probably, and it took a while, so the oxygen can also go to the front side because the cell is a barrier, and the fluorescence is decreased. And this is the way a normal cell should look like. Then on the next slide we have a cracked cell. And there you will see that from the crack positions, also you have the emission of these dark areas. And if the cracks started at the same time the module was put outside, they will have the same thickness to both sides of the crack. from the side of compared to the edge of the cell. You can also see hail impacts. This we've seen with mixed efficiency. Sometimes you see them very well, sometimes not. Probably it is linked to the size of the hail cones. Here clearly you see the typical crack patterns if you have this impact of a hail cone. Also, what you can see here in this special module is that here it's extremely bright. That's in front of the junction box, where modules are typically a bit warmer. And also, what's a bit atypical here is that here in the center of the cell of this module, it's a bit brighter. Typically, you have quite even fluorescence intensity. Here in the centers, it's brighter. And we think that in this module, the additive for thermal aging of the EVA might not have been the best or dosed good enough. But this is just we can't prove it. What we also see, and I also mentioned this a bit earlier, that sometimes we see dark areas around the busbars. So here it's extreme. Nearly every cell has a repetitive pattern where around the busbar you have a dark area. So the first thought would be, quite clear. When you solder, you make a small crack next to the busbar, and that's it. But it can happen, but not in all cases. We have seen a lot of cases where we have this darkening, but we cannot see any electrical problem or crack in electroluminescence in the EL image. So we are not really sure what we see there sometimes. Of course, as you know from, we are probably PV experts, not all cracks are the same. So if you have a crack at the side of a cell, it doesn't have hardly any impact because the area, not all cracks have impact. It depends on whether you have electric conductivity or not. And because of that, it's quite difficult to judge UV images, whether there would be an efficiency loss at a cell or not. So again, a hotspot cell with visible browning, where you even have fluorescence in the red spectral region. This is already shown. And this leads to the case that if you have a large table with extreme hotspots, these hotspot cells will be extremely bright and you can see them from afar. So this is an extreme case. This is a plant that was done from modules that were thrown out somewhere else, but then somebody decided, okay, maybe we should use them for something. They made a plant out of bad PV modules, which is paradise for a researcher, of course. Here, this dark module, it was replaced recently. So here the fluorescence didn't start yet, which is also a nice thing. But here the most important thing is that there are a lot of cells that are extremely hot. We measure temperatures of around 90 degrees at daytime there. At some you can even see that the backsheet is a bit damaged. But these cells are extremely bright. And if you look in the surrounding of such a hot cell, you will see that the brightness of the UV fluorescence, it decreases a bit with the distance from the hotspot. So of course the glass is a thermal conductor and the heat spreads a bit. And here you can see that if some region is heated passively by the cell next to it, that there will be a brightness change because the production rate for the fluorescence is increased with temperature, as most chemical processes. But you can also see in this image, if you look very closely, there was dew on the module because at nighttime very often you have dew, and we wiped it off for the hotspot cell here, but not for the cell next to it. If you have a hotspot cell, sometimes the backsheet will get damaged, which then is a problem because you don't have that isolation that you're required to have for high voltage systems. And the region where you have the damage in the polymer of the backsheet, it's also changing the fluorescence of the backsheet a bit. So you see a color difference, but I don't think that it's very useful to exploit this effect, because these things you see with naked eye as well. What we've seen sometimes in the next slide is that from the busbars you have the fingers, and that some fingers, dark regions, will expand. And my personal opinion, which I can't prove, however, is that some oxygen that might be next to the busbar or some solar flux is conducted in the fingers, because the fingers are quite rough. There's a picture in the next slide where you can see this region that we have pointed out in the whole module in the right top. I think that the reason might be that the fingers, nearly independent on how they are produced, are rough and might conduct soda fluid, and the soda fluid might be a cause of the darkening. So these are microscopic images of different busbar systems, buried contacts or normal printed ones, or galvanic, I think it was in this case, but they have a rough surface. I think that this rough surface moved the solar flux. Then here again we have something for the busbar conduction, where we have dark areas surrounding the busbars. If the slides update, yes. So the prime theory would be that there would be cracks, maybe under the busbar that you can't see because they're electrically connected on both sides, where you have diffusion from the backside towards the front side. The second idea would be that it's based on solar flux that was at these locations much higher, and then just spread it, and due to some strange chemical effect destroys the luminescence. It could be that the busbar is soldered in most parts, but has a small air gap at the sides, or maybe a little bit underneath, where you can have additional diffusion or faster diffusion than through the EVA. And sadly, we failed to prove any of those. Some of what you could use is ultrasound microscope, and we couldn't see any cracks there. In some cases, what we did with electroluminescence, we very often couldn't see any cracks either. However, if it would be directly under the busbar, we wouldn't see that. And we tried with login thermography, where we would see if there are solder problems or the soldering is not done properly, and so there might be indication that there is a gap somewhere. And this also didn't show any good results. What has been known for quite a while, however, is the next image, where you see indoor damp heat aged modules. So you put them in a chamber like for a normal test. Probably a lot of you have these gammatic chambers. What you will see then is that not the core of the cell is fluorescent, but the sides. And this is very common, and this was shown in a lot of journal papers from Beate Röder, Jan Schlotauer. And for this, there seems to be clear chemical evidence that it should be the carboxyl groups. There is a journal paper of Schlotauer from this year, not this year, last year. I think it was in early summer where it got published, where he says that this is due to the carboxyl groups of the EVA. If you have a whole module, it looks like that. It's an extremely weak effect compared to the fluorescence that we have if we have modules outdoor with UV degradation. So here the exposure times are much higher. With naked eye, it's quite easy not to see this effect. And what Jan Schlotauer and Beate Röder very often did, they used a spectrometer to scan over the surface in 2 dimensions to make the analysis of that. Here we've got a cell, the next picture, that is due to the post-processing of the image a bit green. Theoretically it's more like blue, but what you see here in the core is a dark area of the size of a finger. We tried with electroluminescence, we didn't see any cracks there. It could be a small micro crack that could cause something like this. It could be maybe a droplet of some fluid used in the production of the PV module. That's my hypothesis. It could be a fingerprint, maybe that the chemicals in the finger of the salts and so on maybe decrease then later on the fluorescence. But there is no clear evidence to me what causes that. The bright busbars is in the next slide. We have quite often actually. I personally think it's really residuals of solder flux. So typically you have the solder flux to change the surface tension of the solder and to reduce the oxygen, the rust, more or less, of the, sorry for the expression, the rust of the solder. And I think that maybe some solder flux might start increased fluorescence production or decrease it. We've seen both. Here in this case, you see sections where, the next slide, where at the position where I have the mouse right now, you see here that there are extremely bright stripes, and then there are dark stripes. And the dark stripes are even darker than the normal area of the cell, which to me, I have no clear explanation for that, which is a bit sad. But I hope in the future, maybe some of you might find the solution for that. Then, when it comes to other module types like glass-glass or glass-aluminium backsheet, the diffusion that you have from the backside, it's extremely prohibited. There is hardly any diffusion through the aluminium backsheet. And if you have a glass-glass module, you will also have very similar effect where the diffusion can only come from the side. In this case, this was a glass aluminium backsheet module. You see that the aluminium is really working. You see that only at the sides you have a bit of leakage where water or oxygen diffuses into the module. So I think that this is a very interesting kind of backsheet, and you can really see that that it's working. Yeah, of course. Yeah. There are also more exotic findings even that probably you will not see, that we've seen because we looked at a lot of modules so far, for which we have series of explanation which we can't prove. So one thing is that in some cases there are cells that are much brighter but that don't have any visible browning, that are not correlated with any hotspots, and very often these regions of, I would say, duplicated brightness are in rectangular axes. Here you see two examples. This is extremely seldom. But personally, I think that it could be a double layer of EVA. So we have twice the EVA, and twice the EVA might be double as bright. But I could not prove this so far because we were not allowed to disassemble these modules. So we've seen this even outside. In one case in one or two modules of maybe, I would say 1,000 modules that we looked at, we've seen this. So this is how typically it looks. Yeah? Again, short summary, which is not the final summary, but short summary. You can do this in urban environments, roofs of buildings, if it's quite dark. You don't need to alter the electric circuit of the modules, and you can look at the state of the encapsulant. And in many cases, it might be cheaper than thermography. So on the next slide, we have some more strange stuff going on. I will show this because maybe it's interesting for you to see that you can see a lot of things that maybe it's not clear to interpret. So in this case, this was a module that had freshly broken glass. And if you have the breakage of the glass, for sure you have additional diffusion even through the front side to the front layer of the EVA that you would typically see fluorescing. And it's extremely dampened, but not everywhere. And maybe this originates because in the lower section of the module, the glass is more pushed together and less diffusive. But also here we don't exactly know why you have fluorescence in the center of the lower cells, but not anymore in the upper cells. Then we found this strange artifact twice, where you have, well, not even sure how to describe it, a rectangular region in the cell that is brighter with strange core. We've seen this also spread over two cells, so over a cell gap. So it cannot be originating from the cell. And we think it could be a label that was either on the EVA or on the front glass that was peeled off and there was some residual glue. Or it could be the grippers were freshly cleaned with some soap of moving the front glass to the soldered strings of the module. And maybe there was some soap left. That's also quite rare to see that, but we found it. Yeah, here again, you see it on two modules next to each other. I would say that probably it was glue that was on a sticker somewhere on the boxing of a glass. Of course, there are even more exotic things for your entertainment. In this case, that's, I'll wait for the slide update for you. Yes, very soon, hopefully. Yes. So here we had a module that was in the field, and for some reason they put a transparent tape, a sticky tape, on the front side with an X to mark the module. And because it was transparent, they forgot about it and didn't see it for a couple of years. And then it left basically an imprint, seemingly this tape absorbed UV light. And then you see decreased darkness at the locations where this sticky tape was. Then sometimes if you put a module in the UV chamber to make artificial aging, just UV, no increased humidity, so 60 degrees and UV light, sometimes we see these patterns. This is a cracked cell which has a pattern, a bright stripe at some distance of the cell gap, but no fluorescence at the center. And this is also not very clear to us at the moment. And then if you have a silicone laminated module, you see that probably the two different components of the cast silicon were not mixed ideally and have different properties when it comes to UV fluorescence. I have a close-up, I think, in the next slide. And here, this module we treated quite badly for testing purposes. And you see cracks, and these cracks most often are dark, as we would typically expect. But then again, in some sections, there are some cracks that can be described by a brighter line. So if it gets darker with the diffusion of the oxygen from the backside, or brighter, is sometimes also dependent on the encapsulant material or the mixture and component of the two component silicon, which is a bit strange. But it's, as you know, hardly anybody produces that. It was an experimental module. So more or less in the end, I want to talk to you about the camera acquisition and the ambient brightness. So the human eye is quite marvelous. It can see over a lot of decades of absolute radiation. That is, you can measure in lux. So if you would look directly at the sun, you would have 100,000 lux. And then at daylight, it's factor 10 less typically. If you have a photo studio, which is extremely bright, you would be even a factor 10 less. And then it decreases and decreases. So in a typical living room, you have 50 lux. Somewhere between 50 lux and 100 lux, I would say your laboratory will have the illumination typically. And then after sunset, 1 hour after sunset, in German that's called the bürgerliche Dämmerung, the brightness changes quite dramatically. to 3.4 lux typically. Then if you have full moon at night, you have 0.2 to 1 lux. And in these light levels where you have the violet box here, it becomes very difficult to read a book basically. And in this brightness, I would say that you can use UV fluorescence with a normal lamp that you might build yourself or buy somewhere. This is the brightness that you can use this. So it has to be quite dark, much darker than in a normal laboratory, in a normal office. But for example, if you have a small chamber where you can turn off the light, where it's quite dark and you couldn't read a book anymore, you could totally do UV fluorescence in there. The problem now is that the human eye is much better than most cameras when it comes to adapting to brightness changes. If you want to take a picture of this fluorescence, I would recommend to use a full format camera, so €1,000 normal consumer camera, because what you want to image is visible spectra. So you can use a normal camera, but you need to take long-time exposures in the end. So it means tripod, it means ideally remote shutter. A full format camera is 4 times better than a smaller format camera because of just the brighter area, the bigger image pixel size. So 1 pixel gets more light and can create less noise. And if you want to decrease the exposure time, you can also play around with the ISO settings, but again, you will get higher noise. Yeah, it's also quite good to wear dark clothes, because what you can do, you can take pictures, and because you have 30 seconds, you can move around with the camera to illuminate different parts of the region that you have on the camera. You can even walk in front of the camera, because if you have dark clothes, you will not be seen. And by that, you can illuminate larger regions. Yeah, a lot of measurement equipment has fluorescent plugs like multimeters and so on. And this also gives you background illumination. Or sometimes the floor has a lot of dirt, and also then the emission of the floor will be on the module, and this will decrease the contrast. Very often it's good to have the lamp behind the camera. So basically that the visible part of the camera is not blocked. And it's also good that you don't have direct reflections. So even with filtering, you don't want a direct reflection path from the camera to the lamp. So a tilted angle is preferred a bit, like in the next slide. But it's not in no way as dramatic as with thermography cameras. If you have larger sections, what you can do, as I told before, you have the lamp in front of the camera, you hold it and move around, and just use the ability of the camera to take long-time exposure. And if you have a long-time exposure of a moving body, you will see it. If you don't do it properly, for example, if you tilt the light source so that you have a direct path from the light source to the camera, you will have strange artifacts in the image, not sure how you would call them. Of course, this is quite easy to avoid. And if you have a large section, you can mount, it is good to have a lamp that you can mount on a tripod or a monopod or something to move it around in higher regions. Then very often you have, because you have a really large area that you illuminate, you have very weak pictures. So this is the JPEG that you could get out of your camera with a 30-second exposure time of, I think, 5 modules in a big table. Now what you can do not only JPEG acquisition, but also the raw acquisition of the camera, which gives you a better fidelity. And then you can, starting from the raw picture, you can improve the brightness, and then you see much more. Especially, for example, here in the front section at the front bar, or at the corner of the module, you see a lot of dirt that is fluorescing. What you then additionally can do in the dark sections, you can make it even brighter. And with this image processing technique that you can do in not non-typical cases. It's not necessary very often, but only for very large tables, you can get it even in 3 or 4 widths of modules distance to have a nice illumination, or usable illumination. I wouldn't call it nice up there. Yeah, I think we are quite close to time limit. What I want to show you is just 3 more pictures, or maybe a bit more. This is a very old module that was put outside a really long time ago that had strong delamination, and you can even see the delamination with naked eye. Then, if you do UV fluorescence, you can see that the delamination also has an effect on the brightness of the fluorescence. This is the EL image in the next slide. And you see that this is a quite damaged module and quite old-fashioned module. And then in the next slides, you probably will be able to download the slides later on and have a look at it yourself. Here we have a login thermography image, which basically images the heat source distribution. So thermography where you turn on and off the current indoors and look at the amplitude of the variation of the temperature. And there you see extremely well which parts of the cells are heated by electric current. So you can see soldered effects quite well. So in this module, we have not really visible soldered effects, I would say. What you can see is that one bypass diode is short-circuited because 1/3 of the module is missing. Then if you have the EL image, you see that it's a typical module. There are a few cracks in there. And with the UV fluorescence, you will be able to really see the cracks in good detail. But here you see this conduction along the busbars, and this is one of the measurements where we see that we can't really explain why we have these darkened areas around the busbars. For example, here, the mouse is not updating yet, just a second. So here, for example, or here, you see that around the busbars it's dark, and we can't really explain this. However, and this is what I would like to make as a final statement, I think that UV fluorescence is quite novel. It's maybe showing a lot of defects that don't have any real impact in case of energy production, but you can analyze a lot of the modules. So for research centers, I think it's a very interesting tool. If you own plants, I think it's also interesting because you can do measurements at nighttime where you can see the cell tracks with naked eye. I think even for that it's quite interesting. And even if you're interested in polymers, I think it's a fantastic tool. Even if it's, how I use it, it's not quantitative, but only qualitative. But I think it's still very interesting to see and fastly find spots that you want to investigate in further detail. And here I would like to stop and give back the talking option to Franco, so we can decide if there is time for questions. Thank you very much.
Okay, Bernhard, thank you a lot for this very interesting presentation. So the floor now is open for questions. You can utilize chat